Hi, friends. Today I'd like to talk to you about Chapter 7, Sampling Distributions. Here we go. So the topic of Chapter 7 is sampling distributions. And here's the different subtopics we're going to cover. We're going to introduce the concept of a sampling distribution. This concept is going to be, let me get rid of this. The concept of a sampling distribution is going to be critical concept to, or foundational to, the rest of our study of the rest of the book and we're also going to talk about what sampling variability is, sampling error, non-sampling error, and then we're going to look at two different kinds of sampling distributions that are presented in this chapter, and then also some applications of them or some word problems involving those. All right, so as a first example, suppose I go out and ask 1,000 of my students to grab a random sample of 20 library books from the college library and calculate the mean. So the mean weight of a book in their sample. So now I've got 1,000 different samples of size 20, and each one of the students has calculated a sample mean weight. So there's 1,000 sample means. Will all 1,000 students get the same value for X bar, the sample mean weight of a book? What do you think? And the answer to that is no, they won't, because different samples will have different books in them. You're going to get different sample mean weights. This is an example of what's called sampling variability. Okay, so here's your definition of sampling variability. The observed value of a statistic, in this case, X bar, the sample mean, the observed value of a statistic varies or is different from sample to sample, depending on the particular sample selected. And this is called sampling variability. Now, when each one of you go out and get a sample mean weight, again, that's the value of X bar. And there's a population mean weight. And whenever you go out and you get your random sample and you calculate your mean X bar, and after that, we can put together the collection of 1,000 sample means and then average those sample means. And as long as we have a lot of sample means, we could come up with a so-so or fairly good estimate of mu, the population mean weight. Okay, the next thing is this. We want to introduce the concept of a sampling distribution. Okay, a sampling distribution of a statistic, in this case, X bar. It's the entire collection of possible values of X bar, or that statistic, drawn from all possible samples of the same size, N. So going back to the example of the library books where X bar is the mean weight or the average book weight of a sample of 20, in that case, the entire collection of sample means from all possible random samples of 20 library books is called the sampling distribution of X bar. If the library has, say, 10,000 books, then there are 20 choose 10,000 different random samples of size 20. So if we needed the entire collection or the entire sampling distribution, we would have to have this many different random samples and that many different sample means. If you go over to the calculator and you try to compute what this is something like, the calculator will only give you the number in the calculator will only give you the number in scientific notation. So it's something like this, 4 times 10 to the 60 power or 62 power, something like that. So you can imagine how large this number is just by remembering how to convert this number in standard notation to a number, just a regular old number, you would have to move the decimal point on 4. How many places would you have to move it over? Right? 62 times. And each time you move it over, you got a 0 in front. So that is millions, trillions of different samples of size 20 if the library has 10,000 books. But the point that I'm trying to drive home here is that this is your first example of a sampling distribution of X bar. If we had all of the different random samples and all of the different values of the mean that came from those samples, that list of sample means would make up this collection or this sampling distribution of X bar. All right, so there is once again your definition of the sampling, or here's the formal definition of the sampling distribution of X bar. It's just the entire collection of sample means obtained from all possible random samples of the same size, n. Now, in the case of the library example, and for every other case, for every different value of n, we're going to get a different sampling distribution or a different collection of sample means. Later in this section, we're going to present to you what's called the central limit theorem. And the central limit theorem tells us what conditions, under what conditions your sampling distribution is approximately normal. And there's going to be some new notation involved with each one of the problems that we do in the first part of this chapter that has us work with the sampling distribution of X bar. And when we work with those problems, it's important for you to understand the different notations and the different variables that are being used and what they mean. So let's go over that briefly. We're going to be dealing with the sampling distribution of X bar. In this case, your graph of this sampling distribution will be, it could be a histogram or it could be a smooth curve. And your x-axis this time will be an X bar axis. So all of the values of sample mean will be numbers located along the X bar axis. You can think of this picture of the sampling distribution that I've drawn as either being a dot plot for all of the possible different means, or even a histogram. Now, the notation and the new symbols here, okay? This symbol right here, it's mu with a subscripted X bar. We call it, or we pronounce this mu sub X bar. This is a new symbol we're going to encounter now. And this is just the average of the sampling distribution. So remember, the sampling distribution is the entire collection of X bar, or the entire collection of sample means. And whenever you take that entire collection of means and you average them, you're going to get this number, the mean of the sampling distribution. You can also take that entire collection of sample means that make up the sampling distribution of X bar, and you can find the standard deviation for that list of sample means. And that's going to give you this number right here, sigma with the subscripted X bar, or sigma sub X bar for short. Okay, so there's our two new symbols we're going to be encountering. And whenever you're going to see this shortly, is this. For problems that we do involving the sampling distribution of X bar, there's usually two different pictures and several variables involved. So I want you to take a look at the picture. The first picture, you're going to have a population histogram or distribution curve. This could also just be a dot plot of the population. Now here in my picture, I drew a picture of a variable X that is skewed to the right. There's a tail on the right, so it's skewed right. But in general, we may not even know what the population distribution looks like, but that's okay. We can use the theory, the central limit theorem, which I'm going to present later, to answer some questions about, or to do some applications of sampling distributions. But there will always be a picture of your population histogram. It's just the graph of your random variable X, which in this case could be discrete or continuous. Big N is going to represent your population size, And from before, mu will locate the population mean, and sigma will be the population standard deviation. The second picture involved, and the second set of variables involved, will be the graph of your sampling distribution of X bar. And so when it comes to that, you're going to have these four different variables. You're going to have n, which represents the sample size, X bar, which is going to be a particular sample mean. So now in this context, or the context of this problem, X bar is going to be a random variable. And then also you've got mu sub X bar and sigma sub X bar, the mean and standard deviation of the sampling distributions. All right. So another thing I wanted to re-point out that probably went right past you is that for every different value of n, we're going to get a different sampling distribution or a different collection of sample means. And if you take a look, I want you to take a look at this graph over here, okay? It's a series of graphs, okay? And these are graphs of a sampling, these are graphs of sampling of the sampling distribution of X bar. And the sampling distribution of X bar for different values of n is shown here, right? For n equals 30, that's the black curve. For n equals 50, that's the red curve. For n equals 100, that's the sampling distribution curve in blue, and so on. All of these sampling distributions have the same value for mu sub X bar, and they all have the same value. The value of sigma, the population standard deviation, will be the same for all these graphs. And what happens here is, as your sample size gets larger, the sampling distribution graph gets more narrowly centered around its mean. And so what that means is, as the sample size increases, it's right down here. Whenever n increases, the standard deviation of the sampling distribution decreases, and so the graph becomes narrower and spiked up compared to small values of n. So, and you're going to see why this is the case, but in general, we like to have a sampling distribution graph that is as narrow as possible. All right. Let's go over here. I want to show you. Oh, I guess before we do that, let's go over a couple of terms that are presented in the book, section 7.1. And then I want to come over here and take a look at this applet here, which will simulate sampling distributions for us and help us, I hope, be able to wrap our heads around this difficult concept. Okay, so over here in 7.1, there's the concept of sampling error and non-sampling error. So I want to present that briefly, give you an example of that. Okay, so back to my example from the library. Okay, go back to that library example. Remember, I'm going to ask 1,000 of my students to grab a random sample of 20 library books from the college library and calculate the average weight of a book in their sample. Okay, now whenever that is the case, I've got 1,000 students turning in 1,000 different values for the sample mean, X bar. And each one of those values of X bar will be a certain difference away from the actual mean mu. And that difference is called sampling error. So let's take a look at that definition. Whoops, it's over here. Sampling error. It's the difference between the value of your sample statistic and the value of the corresponding population parameter. In the case of the mean and the library example I gave you, the sampling error is just going to be this number, X bar minus mu, or just the difference between the actual value of the mean and the sample mean. And this is the case, assuming that the sample is random and no non-sampling error has been made. The sampling error occurs only in a sample survey and not in a census. Usually, though, in the real world, it's not possible to find the sampling error, the value of it, because the value of mu is not known. If mu is known, then we don't need to find X bar. But the concept of sampling error is very important in making inferences in later chapters. So that's a reason why we're bringing it up now. It's important to remember that a sampling error occurs because of chance. The errors that occur, right? So the sampling error occurs because of chance. It occurs because of sampling variability. The fact that you are all going to get different value for the sample mean, and you're not going to get the exact value for the sample mean. I'm sorry, you're all going to get different values for the sample mean, yes. And if you compare that sample mean, its value to the population mean, it's very unlikely that any one of those sample means will be equal to the population mean. There's always going to be some sort of estimation error. And this is because in your sample won't be 100% reflective of the population. So a sampling error occurs because of chance, the randomness of selecting a smaller subset of the population. The errors that occur for other reasons, however, such as errors made during collection, recording, and tabulation of data, those are called non-sampling errors. These errors occur because of human mistakes and not chance. Note that there is only one kind of sampling error, the error that occurs due to chance or because of sampling variability. However, there is not just one non-sampling error type, but there are many non-sampling errors that may occur for different reasons. So there's your definition of non-sampling errors. We set it up here. It's just errors that occur in the collection, recording, and tabulation of data. And those non-sampling errors can occur both in a sample survey and a census, whereas sampling error can only occur in a sample, not a census. Non-sampling errors rather, can be attributed to many sources: the inability to obtain information about all cases in the sample, definitional difficulties, differences in the interpretation of questions, inability or unwillingness on the part of the respondents to provide correct information, inability to recall information. A respondent may not be able to recall information and have their answer when they're asked the question. Errors made in collections, such as in recording or coding the data, just making a typo. Errors made in processing the data, again, a typo. And errors made in estimating values for missing data. Also, biases resulting from the different recall periods caused by the interviewing pattern used, and failure of all units in the universe to have some probability of being selected for the sample. Okay, that came from the Census Bureau there. And the book also lists, and I thought this was great, some reasons, the main reasons for the occurrence of non-sampling errors. I think you get the gist of it by now, but here's some different, here's 4 different main reasons why these occur. So take a read on that. And let's come down here. The book also gives you an example of a sampling and non-sampling error. Great. And then that's the end of the material for section 7.1. And they just ask you some questions about the terms that were presented there. So what I'd like to do is now come back and talk about the sampling distribution of X bar and also its properties. Okay, the first properties we want to talk about are the mean and the standard deviation of X bar. Let's see. Yeah, let's do it like this. We'll go over these terms and then we'll come over here and I'll try to help you try to wrap your head around the concept of the sampling distribution. No, let's do it now. Okay. All right. So this is Rossmann and Chance have so many great apps. This is one of their applets. I put a link to this over in the module for this week. It's a sampling distribution simulator. Let me zoom in a little bit so you can see it. Well, I don't want to zoom in too much. All right, so we've got different data sets here. I'm going to change this to is it this one? Yeah, here's one. Okay, so right now the size of the population is 18,000. And so each one of the persons in the population has an ID. And they also have a sleep number, which is I believe it's the average number of hours of sleep that they get per night. Okay. And, or this could, I don't know a lot about the data, but this could also be just the number of hours of sleep that the population got on one particular night. And down here, we see a histogram, which is a graph of the sleep data, the number of hours. All right, so this app will let us start sampling from this population. Okay, so I'm going to draw samples of size 10. Let's go with 20 rather. And if I just graph one sample, I just click on draw sample. And then here's that one sample of size 20. I've got the ID numbers and also the actual sleep numbers or sleep hours. The dot plot of that sample is down here. And each one of these dots has a corresponding dot over here from the population, so you can see the location of where the data was taken from. Now over here in this third graph, this is where I'm gonna start drawing a dot plot, or the app will start drawing a dot plot. As we repeatedly sample, this will be a dot plot of the sampling distribution of sample means. Okay, so now if I want to layer on top of that one sample, another 99 samples, so that'll give me 100 total samples. When I press draw samples, it's going to give me three things. Again, the population data, and then this will be the data from the very last of the 99 samples. You can see that the mean was this, and you can see that that's very close to the actual mean. Standard deviation was that, which is also close to the actual standard deviation value. But more importantly, it's over here that I wanted you to. This graph is an approximation of the sampling distribution of X bar. Here we've got a dot plot of 100 different sample means taken from the 100 samples that we just had the computer take. And if we continue to sample, so if I want to layer on top of that, say another, I don't know, 1,000 samples of size 20, then my dot plot starts to look a little bit more normal than it did. And you can see that the mean of the sampling distribution, this is that number mu sub X bar, is awfully, awfully close to the actual mean of the population. And if we continue to take samples, let's take another. So this is 1,100 samples. I'm sorry, 1,100 sample means. Let's take another, I don't know, 5,000 samples. And each time the computer grabs a random sample, it's again going to make put a dot over here and increase the number of dots on our dot plot for our estimation of the sampling distribution. So I'm going to press draw samples and see what happens. Look at the graph of the sampling distribution. It's getting more and more narrow and skinnier and bell-shaped or normal shaped. And notice that the mean of the sampling distribution is getting closer and closer to the mean of the actual mean of the population. So this little exercise has demonstrated a couple of things. One, that the mean of the sampling distribution is awfully darn close to the value of, if not equal to, the value of the mean of the population. Now, the standard deviation for the population, 1.5, okay, that's that's not going to be equal to the standard deviation of the sampling distribution. And in general, this is always the case. It's always the case that the sampling distribution standard deviation is less than the population standard deviation. Also, as this number of samples gets larger, the approximation of the graph of the sampling distribution gets better and better. And we've seen that it gets more as we increase sample size, the approximation gets more bell-shaped. Now, none of these facts are actually coincidental. In fact, they're going to be results of what's called the central limit theorem. All right, let's talk about the first two properties of the central limit theorem here. 7.2. The mean. Okay, so the first property of sampling distribution of X bar is the mean, mu sub X bar. The mean of the sampling distribution of X bar is always equal to the population mean. What this means is that if we have the entire collection of all possible sample means of size 20 taken from this population, then if we average that collection of sample means, we're going to get a number mu sub X bar, and we're going to see that that number mu sub X bar is equal to the population mean, as we can see that that is nearly the case here with our approximation. The standard deviation of X bar, sigma sub X bar, that's also going to be called the standard error of X bar. And you'll probably see why that is the case in the next chapter. Okay, so yeah, this is some information about, this is pretty good stuff here. The sample mean X bar is called an estimator of the population mean mu. When the expected value or mean of a sample statistic is equal to the value of the corresponding population parameter, as it is here for the sampling distribution of X bar, then we say that the sampling or the sample statistic is called an unbiased estimator. So whenever this is the case, whenever your this mean is equal to that mean, the mean of this, you're getting what's called an unbiased estimator. So X bar is called an unbiased estimator of mu. The standard deviation of the sampling distribution, or just called the standard deviation of X bar, that's some number sigma sub X bar, and it's not equal to the population's standard deviation. And we saw that that was the case here, right? The standard deviation of, or the approximate standard deviation of the sampling distribution is this, which is a lot smaller than the population standard deviation. The standard deviation of X bar this is a result that comes from the central limit theorem, which we're going to present in the next section. But this number sigma sub X bar is going to be equal to the population standard deviation divided by the square root of n. And this formula will hold true when the sampling is done either with replacement from a finite population or without replacement from an infinite population. So now that's saying a lot. So we can condense those two statements into the following statement. These two conditions can be replaced by the condition that this formula holds true. In other words, you can find the value of this if you know this, if the sample size is small in comparison to the population size. And the sample size is considered to be small compared to the population size if the sample size is equal to or less than 5% of the population size. So in other words, if this ratio is less than or equal to 5%, then we're going to use this formula here for sigma sub X bar. However, if this statement is false, then we're going to use this formula, this nasty looking formula. Remember, big N is the population size and little n is the sample size. So if this is not true, we're going to find sigma sub x bar with this formula, and this little piece of the formula, that factor is called the finite population correction factor. But what you ought to know is this: in most applications in the real world that we do, but not all of them, but in most of them, the sample size will be small compared to the population size. So consequently, this will be a true statement, and we'll be using this formula to find sigma sub x bar. Okay, so there's two important observations regarding the sampling distribution of x bar, and I've mentioned one of them. Okay, here's the first one. The spread of the sampling distribution of x bar, it's always going to be smaller than the spread of the corresponding population distribution. And that's the case because sigma sub x bar is always less than sigma. And you can also see this for the formula for sigma sub x bar, okay? These two numbers aren't going to be equal. And when the value of n is greater than 1, which is usually true, it's the sample size, then the denominator in sigma divided by square root n is greater than 1, which overall will make sigma over that number smaller than sigma. So in other words, if you increase the value of n, this number will decrease, because as soon as this denominator starts blowing up and getting large, you're taking the overall weight, or which in this case is the population standard deviation, and dividing it by even increasingly larger chunks. So the standard deviation of the sampling distribution of x bar, this number, it decreases as the sample size increases. This feature of the sampling distribution of x bar is also obvious from the formula. And I've drawn you a picture of that. I've shown you before, but let's take a look at it once again. Here it is. So here you've got a series of sampling distributions, all centered at the population mean. And sigma is the same for all graphs because we're sampling from the same population. And the figure shows that if mu and sigma are fixed at specific values, whenever you increase the value of n, the sample size, the standard deviation of the sampling distribution will decrease. And as a result, whenever n increases, the graph will become narrower and more spiked up compared to small values of n. If the standard deviation of a sample statistic decreases as the sample sizes increase, as it does here, that statistic is said to be a consistent estimator. This is another important property that an estimator should possess. So a good estimator should be consistent and also unbiased. And let's see here. Let's see if we can go over to, I think that was all they presented here other than some examples. So the main point of this section was just to introduce the concept of an unbiased and consistent estimator, and also to give you the formulas for the mean, mu sub x bar, and standard deviation, sigma sub x bar, of the sampling distribution of x bar. So that was a bit of a tongue twister there. I dare you to try to say standard deviation of the sampling distribution of x bar like 5 times in a row. It's quite difficult. Let's take a look at some of the homework problems they give us over here. All right, let's take a look at the first exercise here. Suppose x bar is the mean of a sample selected from a population. What is the mean of the sampling distribution of x bar equal to? And part B, what is the standard deviation of the sampling distribution of x bar equal to? Assume that n divided by n is less than 5%. So the answers there are this. Well, the mean of x bar, or the mean of the sampling distribution, is just going to be some number mu sub x bar. And it's going to be equal to the mean, the population mean. The standard deviation of the sampling distribution will follow, that's some number sigma sub x bar, and that's going to follow the formula sigma divided by square root n, where sigma is the population standard deviation and n is the sample size. Because we don't have information about the values of mu and sigma, we can't calculate values for these, but we can say what the values of mu sub x bar and sigma sub x bar will be according to their formulas. Okay, 7.8. What is an estimator? When is an estimator unbiased? And is the sample mean x bar an unbiased estimator of mu? Okay, so the first question, what is an estimator? And an estimator is just a sample statistic, like x bar, that is used to estimate a population parameter. So that's what an estimator is. And an estimator is unbiased when its expected value, or when its value that you expect it to be is equal to the population mean. So that's what we're going to say an estimator is unbiased when its expected value is equal to the value of the parameter it's estimating. And let's see, what was that last question? Is the sample mean x bar an unbiased estimator of mu? And the answer is yes, it is. Since the mean of the sampling distribution of x bar is equal to mu. Okay, question 7.9. When is an estimator said to be consistent? Is the sample mean x bar a consistent estimator of mu? Explain. Okay, so 7.9. We're told that an estimator is consistent whenever the standard deviation decreases as the sample size is increased. And this is the case for the standard deviation of the sampling distribution. So in other words, as n increases, the square root of n in the denominator of the standard deviation formula also increases. And consequently, the value of sigma sub x bar given by sigma divided by the square root n decreases. Question 710 here, 7.10. How does the value of sigma sub x bar change as the sample size increases? Well, we know that it decreases. You've got a situation like this. Let's illustrate that with an example here in Excel, just so you can be convinced of that. Okay, so let's suppose that mu is the population mean, and let's suppose that that is 5. And let's also suppose that the standard deviation is, I don't know, 2. Okay, so this will be for the population. And let's see here. Let's let sample size be a variable here. And we'll take some different values of sample size. Let's go, I guess let's just do it like this. 5. We'll just differ by 5 here. Let me zoom in a bit more. Oops, not that much. Come on now, get down there. Okay, so there's some different sample sizes that are increasing. And now let's calculate the standard deviation of the sampling distribution. We know that that's going to be equal to population standard deviation, which is 2, divided by the square root of the sample size. All right, so let's make Excel do that. This is going to be equal to the population standard deviation, so this cell, divided by the square root of the sample size what happened? It's a typo here. Oh, I didn't close my parentheses, so it didn't like that. Shouldn't be dividing by 0. Oh, I see. I've got the wrong cell in here. I should be highlighting B8. And now I just want to grab and drag and get these other values of the standard deviation for the different. So you're going to have a different sampling distribution graph for each one of these different sample sizes. And before I grab and drag this down, I need to fix in the formula for dragging this down. I need to fix the value of the population standard deviation to be 2. So I'm either going to change the C4 to a 2, or to make Excel know that I want C4 for all my subsequent calculations, I'll just put a dollar symbol in between the C and the 4. Okay, so now I'm going to grab and drag, and look what happens to the, oops. There we go. Come on now. So I hope this convinces you, look, as the sample size increases, all of these numbers decrease. The standard deviation of the sampling distribution decreases. And that's because you've got n in the denominator here. So going back to the answer to this question, we answered it already, 710. The value of sigma sub x bar is going to decrease, right? As n increases, sigma sub x bar decreases, right? All right, let's take a look at 711. In 711, consider a large population with mu equals 60 and sigma equals 10. Assuming that n divided by n is less than 5%, find the mean and the standard deviation of the sample mean x bar. So that they're asking you for the mean of the standard of the mean of the sampling distribution for two different samples, for two different sample sizes, and so for two different sampling distributions. So what is the mean and the standard deviation? Okay, so for part A here, they want values for mu sub x bar and sigma sub x bar. That's all they want. And notice that your book will, look, they're saying, they won't call the sampling distribution of the sample mean the sampling distribution of the sample mean. They just call it the sample mean. So that's kind of, I think, troublesome. Anyways, mu sub x bar we know is going to be equal to mu. And so that's going to be equal to the given value of 60. And sigma sub x bar is going to be equal to sigma over square root n. So in that case, it's going to be 60 divided by, in part A, n is 18. So divided by the square root of 18. And this is about how much? 60 divided by the square root of 18. And we're getting about 14.1. And they want us to play the same game in part B here. Okay, now we've got a different sampling distribution because we've got a different sample size. This time n is 90. So the question is the same in that they want us to give them these two values, the values of mu sub x bar and sigma sub x bar. We know that mu sub x bar is going to be 60 again. But the standard deviation isn't going to be 14.1 because the formula now is going to be this 60 divided by the square root of 90. And where's that calculator at? This is going to come out to be about 6.3. And it's smaller than the 14.1, which we would expect since we increased the sample size from 18 to 90. We would expect a smaller standard deviation for a sample size equal 90 than we would for a sample size equal to 18. All righty. So I think they're playing, let's take a look at this next one, 712. And 712, a population of n equals 5,000, so the population size is 5,000. Has a standard deviation of 25. In each of the following cases, so there's two different questions here, A and B. In each of the following cases, which formula will you use to calculate sigma x bar and y? Okay, so what do we need to check? We need to check is little n divided by big N less than or equal to 5%. Okay, so I'm going to check that for the part A here. So for part A, n divided by big N, so that is going to give us 300 divided by 5,000. And let's see, what does the calculator say that is? I think that's 6%. Is 6%, is 0.06. So this is a false statement then. So therefore, we need to put in there the finite, what is it called? The finite population correction factor. What the heck is that thing called? We need to put in, yeah, the finite population correction factor, or in other words, we should use this formula. So therefore, sigma sub x bar should be sigma divided by square root n. And you don't have to memorize any of these formulas, by the way. You just make sure to, when you're making a formula sheet for your test or your quiz, make sure you've got these formulas written down and note what they mean, okay? So here we're gonna use this, it'll be this number times that finite population correction factor, which is the square root of big N minus little n over big N minus 1. So let's plug the values in there. That is going to be 25 divided by 300 under the square root. Oops. And then all of that is going to be times this square root of, well, we got to go big N minus little n. So 5,000 minus 300 divided by big N minus 1 would be 5,000 minus 1. So we'll run that through the calculator now, see what we can get. And I'm getting that this is about 1.4. So I'm approximating. This is about 1.4. So then for part B here, this is again 712. For part B, it's the same question. Which formula will you use to calculate sigma sub x bar and why? So we're going to say here, I guess I better go back up here. Since n over big N is not less than or equal to, and how do you say not less than or equal to? Well, you just put a slash through that. 5%, we use this formula here. And in part B, N is equal to 100. And big N over little n, oops, it's the other way around. Little n over big N is 100 over 5,000. And that came out to be, how much was that? I think it was less than 5% here, 100 divided by 5,000. But that came out to be about 2%. So I'll just put a period there. And we'll just say this, since little n over big N was less than or equal to 5%, we use the formula sigma x bar equals sigma over square root n. And that's just going to be equal to 25 was the given standard deviation of the population divided by the square root of 100. So that's going to come out to be 2.5. And but once again, remember, in most cases that we deal with, this will be true. And so in most cases, we're going to use this formula here. But just notice that, and just remember that in practice, if this is not a true statement, then we've got to put on that factor, that population correction factor. All righty. Take a look at the next one here. It's 713. That one's not very interesting. Let's just do part A. I don't see me putting one of those on the test. Okay, so 713, I'm just going to do part A. It's just some algebra business here. Okay, so part A. We're told that the population mean is 125. Sigma, the population standard D is 36. Okay, fine. For a sample selected from this population, suppose that mu sub x bar is 125. That's no surprise that these two things are equal. And also suppose that sigma sub x bar is 3.6. And again, no surprise that these two things are unequal. And then they want us to find the sample size, assuming that n over n is less than 5%. So since this is just some algebra business, I'm not very interested in this question, but we'll do it anyway. Since n divided by big N is less than or equal to 5%, sigma sub x bar is equal to sigma divided by square root n, or equivalently, this is going to be equal to 3.6, right? Because sigma sub x bar is 3.6. And then that's going to be equal to 36, because sigma is 36. And then we're going to divide that by the square root of n. And then we just need to solve this for n now to answer this question. So this is just some algebra business. I really am not that concerned about it, but we'll do it anyway. So to solve this, we're going to multiply both sides by the square root of n. So then 3.6 times the square root of n is equal to 36. And now divide both sides by 3.6 so you can isolate the square root of n. And that is going to give us, let's see, I believe that is going to be, oh gosh, Tim, 10. Okay. This is not good form. Or that the square root of n is equal to 10. Now, if we square both sides, then we're going to get that n is equal to 10 squared, or n is equal to 100, and that's what they wanted. So not a very interesting question in terms of statistics. Let's take a look at some of the applications here, and then let's move on so I can show you how easy it is to do the other problems in this section. All right, here's this first application, 714. The living spaces of all homes in a city have a mean of 2,300 square feet and a standard deviation of 500 square feet. Okay, so right there, we're talking about living spaces of all homes in the city. So that is giving us a value for population mean and standard deviation. So these values are given. Mu is 2,300, sigma, the population standard deviation, 500 square feet. Let X bar be the average living space for a random sample of 25 homes selected from the city. So n is equal to 25 now. Find the mean and standard deviation of the sampling distribution of X bar. So they're just saying, hey, give me values for mu sub X bar and sigma sub X bar. Alrighty, so we know that mu sub X bar is going to be equal to mu, and so that's just going to be the value 2,300 square feet. And we don't know what the population size is, but it's likely that n divided by big N is less than or equal to 5%. And that's because you have such a small sample size. You've got 25 is a little n. And if you're talking about all the homes in a city, well, a city is going to have a heck of a lot larger than 25 homes. So it's likely that this sample size is very small in comparison to the population size. And so therefore, I'm just going to use sigma sub X bar equals sigma over square root n to find the standard deviation of the sampling distribution. So that's just going to be 500 divided by square root of 25. So that's 500 divided by 5, and that's going to give us 100. So that's what they wanted. Just give me the values for mean and standard deviation. So they're playing the same game over here as well. Let's take a look. 715. According to the 2019 Physician Compensation Report by Medscape, American orthopedists earned an average of $482,000 in 2019. Suppose that the mean and standard deviation of the 2019 earnings of all American orthopedists were $482,000 and $90,000 respectively. So they just told us there, right? The values for population mean and standard deviation. And what is it that they want? Well, it's the same as that last question. Find the mean and standard deviation of the sampling distribution, assuming n over n is less than or equal to 5%. So that's easy, right? Mu sub x bar is just equal to mu, right? It's the same as mu. And sigma sub x bar is going to be sigma over square root n, right? So it's just going to be 90,000 divided by the square root of, what was their sample size? 200. And that is whatever that is. Let's find out. Where's that calculator at? Square root of 200. I'm getting this is about $6,363.96. So that's all they wanted. And I think the rest of this, what was the deal here? Okay, so this one, I'm not very interested in these questions here. They just want you to show that this shortcut formula here will also give you the same as this. Well, let's see here. It doesn't give you the same as that. And that's probably has something to do with the fact that this is not less than 5%. So I'm not really interested in that very much. Okay, let's go to the next section. And the next section will talk about what's called the central limit theorem. We're going to get three things from that, three pieces of information from the central limit theorem. And the first two pieces of information we've already been given, which were nothing but the formulas for mu sub x bar and sigma sub x bar. The third thing that we're going to get from the central limit theorem is a description of the shape of the sampling distribution. All right, so let's get on right on down here. Okay, so there's a couple of cases to consider. Okay, the first case is when your population is normally distributed. Assume for a second your population is normally distributed. Okay, if the population from which the samples are drawn is normally distributed with mean, mu, and standard deviation sigma, then your sampling distribution of sample means, x bar, will also be normally distributed, where the means and standard deviation of the sampling distribution are given by those formulas that we know and love. Okay, so that's no big deal, right? If your population is normal, then your sampling distribution is also going to be normal, no matter what your sample size is. No matter what your sample size is. And so the author gives us a sequence of graphs here, which also illustrate that X bar is a consistent estimator. Here's your population distribution graph. And then here's graphs of the sampling distribution of sample means for increasing values of n. And you can see that all four of the graphs will be centered at the same place, mu, along the x-axis. But the standard deviations are going to be different, as depicted by the different amount of spread in each figure. And you can also see that as the sample size increases, that the normal distribution describing the sampling distribution gets smaller and more narrowly centered around the population mean. But what about the shape of the sampling distribution when your population graph is not a normal curve because this happens. Well, let's talk about that. According to the central limit theorem, for a large sample size, and by large, we mean something that is greater than or equal to 30. For a large sample size, your sampling distribution of X bar will be approximately bell curved or normal in shape, irrespective of the shape of the population distribution. So the central limit theorem tells us that even if you don't have a population that's normally distributed, and even if you don't even know what the shape of the population histogram or distribution looks like, as long as your sample size is greater than or equal to 30, your sampling distribution will be approximately normal. Okay, so take a look at a couple examples over here that illustrate these properties. Okay, let me give me a skewed graph here. First, here's a population. This is again those sleep numbers, or the amount of sleep that the population got in a single night. The population size is 268. Okay, good. It's 18,000. There we go. All right, so I'm going to use that data. There's the graph of the population histogram. It looks like it's going to be normal. It looks like it's normal, right? And if over here, remember, we can sketch estimates of the sampling distribution of X bar. And let's see here. Let's take small sample sizes of, say, 5. Okay, and then just give me a sketch of, say, I don't know, 1,000 random samples. Okay, so we took 1,000, or the computer took 1,000 random samples of size 5. This graph is the dot plot of the most recent sample of size 5, which gave you an average of 7.6. Population average was 8. And we took those 1,000 samples, and the computer listed all 1,000 sample means, and then graphed those sample means as a dot plot, which gave us this curve here, which you can see is it's an approximation of the sampling distribution graph, and you can see that it's normal. It's roughly normal. And I guess what I'm trying to illustrate here is, let's change this to 50, and let's reset this. I guess what I'm trying to illustrate here is what the book was saying, that look, if your population graph is approximately normal, then it doesn't matter what your sample size is going to be, your sampling distribution graph will be approximately normal. Okay, the other point the book was just trying to make, let's take a look at this example. I've got a second variable called sleep2. It's also the sleep numbers for 18,000 people. Maybe this is on a different night. And so this is the graph of those sleep numbers. You can tell that that population data is skewed to the right, skewed right, since there's a tail forming on the right. So it's skewed. And let's change our sample size to, say, I guess size 5, so small, and then sketch those samples. It looks like the sampling distribution curve it's almost normal, but look, it's also got that tail coming out to the right. So if you've got a population that is not normal, and you've got a small sample size, something less than about 30, then your sampling distribution is not guaranteed to be approximately normal. So in the case of the mean, we consider the sample size to be large if n is greater than or equal to 30. So again, the central limit theorem, what does it say? It says that if you don't know what the shape of your population data is, which in a lot of cases is the case, or if you know what the shape of it is and you know that it's not normal, that you know that the sampling distribution will be approximately normal, so long as the sample size is greater than or equal to 30. All right, so now I'm going to reiterate some of the things I said right here. Note that when the population does not have a normal distribution, the shape of the sampling distribution is not exactly normal, but it is approximately normal for a large sample size. The approximation becomes more accurate as the sample size increases. Another point to remember is that the central limit theorem applies to large samples only. In the case, usually in the case of the mean, if the sample size is 30 or larger, it is considered sufficiently large enough so that we can say the central limit the theorem can be applied to the shape of the sampling distribution. So go back over here, same data set, population is skewed right. Let me reset this. Whenever I have a sample of size 30 or larger, let's make it 50 here. And you can see, oh, the graph is approximately normal now. It's got tails on both ends. So I'm trying to illustrate that point. So here's some points from the central limit theorem, or from this statement. When n is greater than or equal to 30, the shape of the sampling distribution of x bar is approximately normal, no matter what the shape of the population data looks like. And this is a result of the central limit theorem, which was a proven theorem. We can't show you the proof in this class because it's outside the scope of this class, and we don't have the tools in our tool belt to be able to understand it anyway. Also, the mean of x bar, mu sub x, it will always be equal to the mean of the population mu, and the standard deviation will be equal to sigma over square root n if this percentage is less than 5%. So again, remember, for sigma sub x bar equals sigma over square root n to apply, n over big N must be less than or equal to 5%. Otherwise, we multiply that sucker by that finite population correction factor that we had to do for that one problem. So the author does give us a series of graphs here. Here's a graph of a population that's skewed right. The sampling distribution of x bar for small sample size of size 4, you can see that's also skewed right. The sampling distribution for samples of size 15 also skewed right, but starting to get more normal as n increases. And once you get to about 30, the sampling distribution is approximately normal. Oh, they have an interactive applet. I didn't see that. We'll have to play with that. Okay, what's going on? What's going on here? They've given us the fixed values for mean and standard deviation. And it looks like this is the sample size over here. So if I increase the sample size by grabbing this dot and making it larger, you see what happens. The sampling distribution gets skinnier and skinnier and more normal. So I guess that's all they wanted to illustrate. That was kind of cute. And there's some examples, and I think just one example, but let's give you some examples by doing some of the exercises here. All right, 718 here says, what condition or conditions must hold true for the sampling distribution of the sample mean to be normal when the sample size is less than 30? And the answer to that, we know from the reading, is that the sampling distribution will be normal when n is less than 30, only if the population is approximately normal. And also, it turns out that if there's any sort of symmetry present in the graph of the population data, you're also going to get a normal sampling distribution for small n. All right, so I'm going to try to summarize that here. Yeah, so whenever n is less than 30, the sampling distribution of x bar is approximately normal only if the population distribution or the population histogram is normal. or if it has any symmetry. So this last little piece that I added on there, the book doesn't tell you that, but that is true. Okay, and then for 719, explain the central limit theorem. Okay, well, they just want us to regurgitate the statement of the theorem. Okay, and they have a great, they've summarized it right here. For a large sample size, in other words, if n is greater than or equal to 30, the sampling distribution of x bar will be approximately normal in shape, and the mean and standard deviation of the sampling distribution, these numbers, mu sub x bar and sigma sub x bar, will be given by these two formulas, mu and sigma over square root n. All right, let's take a look at 7.20 here. A population has a distribution that is skewed to the left. Okay, fine. So the graph looks kind of like this. Whoops, tails on the right, so skewed right. So no, it looks like this. Something like that, maybe. It's skewed left. Tails on the left, so it's skewed left. Indicate in which of the following cases the central limit theorem will apply to describe the sampling distribution of the sample mean. And of course, we know that that's only the case when n is greater than or equal to 30. So only n equals 400 and n equals 36 will apply. And I think it's the same question here. A population has a distribution that is skewed to the right. The sample size n is selected from the population. Describe the shape of the sampling distribution. Oh, did they want us to do that here? Describe the sampling distribution. No, but here they want us to describe the shape of the sampling distribution. Okay, that's no problem. So in 7.21, we know that the graph is skewed, of the population is skewed to the right, so something like that maybe. And they want us to describe the shape. So in A, since n is less than 25, the shape of the sampling distribution will probably be skewed right as well. And for B, since n is larger than 30, the graph is normal. The standard deviation, or the sampling distribution graph is normal. Is approximately normal. And for C, it's the same as A. This should say n less than 30. Shame on me. Well, sometimes when you're talking and writing, you don't get it all right at the same time. So A and C are the same answer. We're going to say skewed right, since n is less than 30. Pretty exciting stuff, huh? Let's take a look at some of these applications here, or word problems. 723, let's take a look at that one. The delivery times for all food orders at a fast food restaurant during the lunch hour are approximately normally distributed, with a mean of 7.7 and a standard deviation of 2.1 minutes. Okay, so right there, they told us that the random variable x is representing delivery times during the lunch hour. So during the lunch rush. And they also told us that if you graph X, either the histogram or as a curve, either way, you're going to get a normally distributed graph. So the population distribution looks like a normal curve. And moreover, they told us that it's centered at mu equals 7.7 minutes. So the average delivery time was 7.7 minutes. That's pretty good. And they also told us that the standard deviation is 2.1 minutes. Okay, fine. And then what's the question? Let X bar be the mean delivery time for a random sample of size 16 orders at this restaurant. Calculate the mean and standard deviation of X bar and describe the shape of its sampling distribution. Okay. Since n is equal to 16, or let's say it like this, it doesn't matter that n is 16. Since the population is normally distributed, the sampling distribution graph will also be normally distributed, no matter what the size of the sample. So what is it they want? No, they want us to describe the shape. We did that. And they also want values from mu sub X bar. Well, we know that that's just going to be 7.7. And they also want a value for sigma sub X bar. And let's see here. So we're going to assume that 16 is less than 5% of the total population size. So we'll use sigma over square root n. So in most of the problems that we do, we're going to use this formula. So if they don't tell you anything about the value of the population size, just use this formula here. And that's going to be what, 2.1 over the square root of 16. So that's going to be 2.1 divided by 4, which is about 0.525 minutes. So that's all they wanted. So, and the rest of these, there's only what, 2 or 3 of them? I believe are asking the same, pretty much the same question there. Just describe the shape, because that's all this section was about. Describe the shape of the sampling distribution. So now I want to get on to the meat of the first part of this section, which is section 7.4. In 7.4, now we're going to be using sampling distributions to find probabilities. That's the entire objection here, or objective rather. Calculate and interpret improbabilities for the sampling distribution of X bar. Here we go. Let's try all the way down here to the homework here. I'll come back to those first 2. I'll come back to those as well. Well, I guess we can just talk about it first. All right, so to answer these 2, let's see here. Okay, so to answer these 2 questions, what the book does at the first part of this section is they apply the empirical rule. They apply the empirical rule to the sampling distribution of X bar. Whenever that sampling distribution is normal, you can apply the empirical rule to it. So the empirical rule will apply to the sampling distribution will give us these 3 statements. 1, that about 68% of your sample means will fall within one standard between these two boundaries, which are one standard deviation above and below the mean. Also, about 95% of all sample means will be within 2 standard deviations of the actual population mean, or between these two boundaries. And 99.7, or nearly all of your sample means will be within 3 standard deviation lengths, or between these 3 boundaries here. Okay, and the other thing we're going to need for these 2 questions is the z-score of a particular value of x bar. Okay, so remember, the sampling distribution of x bar is the entire collection. It's just a list of all of the possible sample means x bar. And each one of those values of x bar will be our numbers along the x bar axis on the sampling distribution curve. And each one of those values will be a certain distance away from the actual value of mu. You can, the z-score, you can find the z-score of any one of these x bar values with the z-score formula. And it's just going to represent the number of standard deviation lengths that a particular x bar is away from the population mean. So the formula for z is x minus mu over sigma. But now if you apply the z-score formula to x bar, then instead of using x in the formula, you're going to be using x bar. And instead of using sigma in the formula, you're going to be using sigma sub x bar. So really this denominator is sigma over square root n. All right, let's take a look. Now that we've got those in our arsenal here, take a look at this first question, 7.28. Okay, so if all possible samples of the same large size are selected from a population, what percentage of all the sample means will be within 2 standard deviations of the population mean? All right, let's take a look at the answer to that. Let me draw a picture. All right, so we know that the sample size is large, so larger than 30. And so that means that the central limit theorem applies, and that means that the sampling distribution is approximately normal. Moreover, we know that it's centered at mu. And the question is asking us, okay, there's 2 boundaries. There's 2 boundaries. One is right here, and the other one is right here. And these 2 boundaries are 2.5 standard deviations away from the mean. So that means that this first boundary is mu plus 2.5 standard deviation lengths, so 2.5 times sigma sub x bar. And this number here is mu minus 2.5 standard deviations, or 2.5 times sigma sub x bar. And the question is what is this percentage? What is that percentage? Right, you've got all the values of x bar along this axis, and they're trying to get you to find what percentage of sample means will be between this boundary and that boundary, or in other words, within 2.5 standard deviations of the mean. Okay, so one way to do this problem is to involve z-scores and to use the standard normal distribution. So that's what I'm going to do now. Show you how easy that is to do. So they want us to, in symbolics, they want us to do this. Find the probability. This is a nasty looking symbolic statement here, but find the probability that x bar is between these 2 boundaries here, mu minus 2.5 sigma sub x bar and mu plus 2.5 sigma sub x bar. All right, so we don't even know what the values of mu and sigma are. So how can we do this problem? Right? Okay, well, the way to do it is use z-scores. Okay, this is how we do it. Okay, I'll make a table here to try to help illustrate this. We've got two different x values here, and we want to find their z-score. And that's going to be given by the formula x bar minus mu over sigma sub x bar. Okay. So we'll see what happens. These two boundary values, the first x bar value will be this boundary value, mu minus 2.5 times sigma sub x bar. And this other one will be mu plus 2.5 times sigma sub x bar. And look what happens to these z-scores, okay? All right, so the value in the x bar in the formula is going to be this number now. Okay, so it's going to be mu minus 2.5 sigma sub x bar, and then minus mu over sigma sub x bar. Right, this number on this boundary is a value of x bar, and it's the value of x bar, which is mu minus 2.5 standard deviations, okay? So I plug that value in for x bar into the z-score formula, and I get this. And we can remove those parentheses, subtract mu from mu, and then the numerator is just negative 2.5 times sigma sub x bar, and then the denominator is sigma sub x bar. Now the sigma sub x bars will then divide out, and we're left with the z-score of negative 2.5. And a similar thing is going to happen with this z-score of this x bar value. It's going to give us 2.5. And you can see that here. So that's the setup of the formula. You can subtract mu from mu, and then we're getting 2.5 sigma sub x bar over sigma sub x bar. The sigma sub x bars will divide out, and you're just left with 2.5. Okay, so now what we're going to do is use the standard normal curve. Okay, so the probability that mu minus 2.5 sigma sub x bar, or we want to write it like this, that x is between those two boundaries, mu minus 2.5 sigma x bar and mu plus 2.5 sigma x bar, but that's just equal to the probability that z is between negative 2.5 and 2.5. I have to work on writing my fives here. And so now I can get this probability from, you can use the z table, but I recommend against it. Let's just use technology, shall we? Where is that calculator that I started to like? I think it was the Rossmann Chance one, wasn't it? Oh, but for the between ones, I think we found that it was better to use the GeoGebra calculator, or easier anyways. So let's go over there and find that sucker. It's just this link here. Okay. So change this to a normal. I've got mu and sigma at 0 and 1 like I want to. So I've got the standard normal distribution, and now just change this number to negative 2.5. Right, and this number to 2.5. And we're done about 98%, 9876. So about 98% of X bar values will be within 2.5 standard deviations of the mean. So that's that problem. I believe that 7.29 is similar, very similar, and they're giving you the solution here. They just find the z-scores of these two boundaries, which are negative 150 and 150, and then they take it over to the calculator. So let's skip that one since it's similar. And let's go on down to 7.30 here. In 7.30, we can use Excel. All right, so for 7.30, assume a population. For a population, the population size is 10,000. Okay. Population size is 10,000. Okay, fine. Population mean is 124. Population standard deviation is 18. Okay, fine. Find the z value. Okay, so we're going to assume n is 36. And they want us to find the z-score of each one of these sample means. Okay, so for that, I would just use Excel since I can get the answers pretty quickly here. Let's open that up. And let me get another sheet here. And I'm going to need the book. Slide this over then. Oh. There we go. Okay, so I'm going to write in the values here. Let's see here. First thing is we need to check and see which formula we need to use for the standard deviation. So I'm going to calculate a value for n over big N. And it looks to me like it's going to be super small, less than 5%. So it's 36 over 10,000. And that's certainly less than 5%, isn't it? 36 over 10,000 is 36, 36 10,000s, which is less than or equal to 5%. So sigma sub x bar will be given by the formula sigma divided by square root n. Okay. All right, so that much we know. Getting back over here, let's see here. Let's put in the values here. So mu and sigma and n. All right, so those three values are 4, 18, and 36. Okay, fine. And then the value of sigma sub x bar, the standard deviation of the population, that's going to be given by the formula sigma divided by square root of n. All right, so let's put that value, I guess, right here. So let's see here. That is just going to be equals to sigma, and then now divide that by square root of 36. Close that parentheses. Okay, I did that. And it gave us 3, a real nice, easy, happy number. Alrighty. So now I'm going to put the values of x bar in. And then next to those, I'm going to find the corresponding z-scores, which are the answers that we're looking for. Alrighty, so could I just copy and paste these? No, it doesn't want me to do it. All right, fine. Okay, so double check I've entered those incorrect, looks good. So now I'm going to type in the z-score formula. And so that's going to be equals to, I'm going to use parentheses for my numerator. It's the value of x bar, in this case, minus the mean, the population mean. And then we want to divide that by the standard deviation of the sampling distribution, this number. Now, before I drag and grab and fill, I need to make sure that Excel will keep the values of sigma sub x bar at 3 and the value of mu at 124. So to get that done, notice I've got this cell highlighted, and I'm either going to go up there and just change B1 to the number 124 and change the E5 to the number 3, or I can just put a dollar symbol between the B and the 1 and the E and the 5. Then Excel will know to keep those values fixed at 124 and 3 as I grab and drag and fill. And couldn't successfully grab it, I guess. There we go. And there's my answers. Boom. There's my four z-scores for each one of those 4 values there. Alrighty. So that's that one. And z-scores are usually rounded to the hundreds. And that's because the z-table has the z-scores rounded to the hundreds. So when I write down these answers, I'm going to approximate all of them to the hundreds. All right, so the meat of this section is now going to just be asking us for probabilities, okay? Let's take a look at the next one. And it's 7.31, okay, fine. Let x be a continuous random variable. It has a normal distribution with mu equals 75 and sigma equal 14. Did I write down 75? No, I wrote down 74. Oh boy. Alrighty. Assuming n divided by n is less than 5%, find the probability that the sample mean x bar for a random sample of 20 taken from this population will be A, between that and that. Okay, so there's a lot going on there. So we know a couple of things here. A couple of things we know here are this. Since x is normally distributed, the sampling distribution is normal. Now, you don't have to write this into your answer if you're doing this problem, but I'm using this as a teaching moment, so I am. Okay, so we know that the sampling distribution is normal. And also, since n divided by big N is less than or equal to 5%, we know that sigma sub x bar is just going to be given by the formula sigma divided by square root n. Okay? And they want us to assume that the sample size n is 20. And for part A, they want us to find this probability. Find the probability that x bar, a randomly selected x bar, is between the two numbers they gave us, 68.5 and 77.3. And in part B, they want us to answer the question, find the probability that x bar is, this time it's x bar, is less than, this just says between, not between and including, although those two things are equivalent. I'll just write down the right thing here. So this one, the probability x bar is less than 72.4. Okay. Alrighty, so what I'm going to do is I'm going to calculate a value for sigma sub x bar. And I'm also going to write down the values for mu sub x bar as well. So we know mu sub x bar is equal to mu, which is 75. And sigma sub x bar is sigma over square root n. So that's just going to be 14 divided by the square root of, in this case, n is 20. And let's get an approximation for that. It's not going to be a happy number. 14 divided by square root of 20. So that is roughly 3.13049 and some change. Now, because I'm going to use this number in a subsequent calculation, I want to make sure that I have a good approximation of this number. And that's why I'm taking so many decimal numbers, or that's why I'm taking so many numbers to the right of the decimal point in my approximation. All right. So to answer question A, hey, it's going to be easy. Just let's get on over here to this probability calculator, the one that handles the between ones very well. I guess let me restart it just so I know it might work right. So change this to a normal, and we're going to locate the sampling distribution. So mu is 75. And sigma should be this number. So change that. Point, what is it? 130495. And then we'll change these two numbers to 68.5. This one, don't quit on me, 77.3. And bam, I got the probability. It's this number right here. We are done. We are done. 0.7498. So about 75%. About 75% of sample means will be numbers between these two values. And if we want the probability X is less than 72, then we want the less than, the left-sided here. And I'll change this number. Will it let me? To 72.4. And I'm getting that this is about 20%, 0.2031. And that's that. And that's that. So now how the book does this problem is they use the z-table. So how the book does this problem is, hey, you find the z-scores for these two guys, and then you find the area underneath the standard normal distribution curve between these two guys' z-scores. We don't need to do all that work, right? Just use technology, right? Okay. So I want you to practice these questions and practice all of the questions. Between chapter 6 and 7, there's a lot of similarities. We're using the calculator. We're using normal distributions. But you have to be careful as to what the question is asking. Here, they're asking us a probability question about a sample mean, which means that when we go to use the calculator and we put a value in for sigma, we better be using sigma divided by square root n and not 14 and not sigma. Okay, so be careful. That's one common mistake that students will make here. All right, let's go back over, and the rest of these questions are similar to that now. I guess let's do a couple for good measure. So all of these ask you to find probability. We'll do a couple of those for good measure. All right, let's take a look at these two, 7.38 and 739 here. This is your typical question here in this chapter. Okay, so what is it? The amounts of electricity bills for all households in a city have a skewed probability distribution with a mean of 140 and a standard deviation of 30. So when it says it has a skewed probability distribution, we know that if you can draw a histogram and then draw a smooth curve over that, then it would just probably be a histogram that looks, what is it? It's skewed. Oh, it doesn't say whether it's skewed left or right. So I'll just draw a generic skewed right graph for the value of X. And I know I haven't read the question yet, but that's because I just want to write down what I was given, okay? We know that X, this is our population graph, and X is a list of all the electricity bill amounts. And let's see, we were told that the mean and standard deviation of the population were given at 140 and $30. Okay. So they want us to find the probability. So find a probability, right? That the mean amount of electric bills for a random sample. So that means a sample mean. Find the probability that a sample mean taken from a sample of 75 will be between 132, that number and that number. Okay, so parts A, B, and C. So we're going to assume n is equal to 75, that was given. We are going to assume that the sample represents less than the population size. I'm sorry, the sample represents less than 5% of the population size. So sigma sub x bar will be sigma divided by square root n, which in this case will be 30 divided by the square root of 75. Let's get a value for that. We're getting this is about 3.464101. Okay. Now for the questions. Okay, so for part A, remember the question is find a probability about a sample mean. Find the probability that a mean for a random sample, so that means x bar. Find the probability in A that x bar is between those two numbers, 132 and 136. And for part B, find the probability that, okay, so this one a little tricky. So now we want to find the probability that x bar is within $6 of the population mean. So that means either $6 within $6 above or within $6 below the mean. So that's asking us to find the probability that x bar is between, I'm just going to take the mean and subtract 6. So between 134 and add 6 to the mean and 146. So that'll give us the probability x bar is within $6 of the population mean. And then for part C, find the probability that x bar is what? More than the population mean by at least 4. Okay, so greater than or equal to, at least is a greater than or equal to. Greater than or equal to the mean 140 plus $4, so 144. That's what they want. And to get these three probabilities, we are going to go over and use the calculator. So now we're not going to use, when we use the calculator, we're not going to use the population graph, right? Rather, we're going to be using the graph of the sampling distribution, which we know is normal since the sample size is greater than 75. And we just want to find the area between, let's see here, if mu is 140, then there's the center. And we just want to find this little area here in part A between 132 and 136. We just want that little area there. And if this is the sampling distribution graph, this is the x bar axis. All right, so let's get on over to that calculator. Well, I guess I'll try this one again. It seems to be working okay right now. And it's good to use this one for the ones that are between. So let me go over to a normal distribution, just change this. I want the sampling distribution graph. So I've got to tell it that mu sub x bar is, well, 140. That's no problem. But the standard deviation here, since this is supposed to be the graph of the sampling distribution, the standard deviation needs to be this number sigma sub x bar. So let's put that in 3.464101. And let's see, change these numbers for part A to 132 and 136. So there's my shaded area, and then there's my probability. This is about 11%. And to do part B, all I need to do is change the numbers, the endpoints here, to 134 and 146. And then the probability will change to about 91%. And then for the greater than or equal to, I'm going to click on the right-sided and then just change this number to 144. And it gives me this area to the right, which is what I want, and that's about 12%. So that's how you find probability for a sampling distribution of X bar. For good measure, let's do another one. And let's try this one, 739. According to Experian.com, the average household mortgage debt was $2,002, $202,284 for the first quarter of 2019. So that was an average. Suppose that the current distribution of mortgage debts of all U.S. households has a mean of this and a standard deviation of that. All right, so here X is going to represent the random variable, which is the household mortgage debt. And the population mean mortgage we're assuming is 202,284. And standard deviation is $36,000. Okay, now the question. Find the probability that the current average mortgage debt for a random sample. So find the probability that a current average mortgage debt for a random sample. So this is asking us to find the probability about a sample average X bar. So if the sample is size 144, they want us to, in part A, find the probability that the average for a sample, so it says it right there, the average for a sample, so that's X bar, is less than 198. I think they meant to say 1,000. They got a typo there. And for B, more than, so the probability X is greater than, X bar is greater than 206,000. And then for part C, find the probability that X bar is between 200,000 and 205,000. Okay, so we can use the central limit theorem, which will tell us that the sampling distribution graph will be normal, and it will also give us values for the mean and the standard deviation of the sampling distribution. So here, mu sub X bar will be always equal to mu, 202.284. And the standard deviation of X bar, we're going to use sigma divided by square root n. And that's because, let's see, 144 is certainly less than 5% of the total number of households that have a mortgage. So we're going to use this formula for sigma sub X bar, and that's going to give us 36,000 divided by the square root of 144. So that's 36,000 divided by 12. Okay, so that is going to give us 3,000. All right, so these are the two values we need to use in the calculator. So we have no idea what the shape of the distribution of X looks like because it didn't say. But that doesn't matter because the central limit theorem says that since the value of n is larger or greater than or equal to 30, we know the sampling distribution graph for samples of size 144 will be approximately normal with mean equal to that and standard deviation equal to that, okay? And that's why we can use the probability calculator that has the normal distribution in it. So I'm going to set my value of mu here, 202.284, and the value for the standard deviation now, careful, it has to be this number, the standard deviation of the sampling distribution, not this number, not this number, this number. No, not this number, this one, okay? Careful now. That's a typical student mistake, I would say. So if we want a less than, I guess we'll click on the left-sided and see if this thing will work out for us. Change this number to 198,000. We got the right picture. We got the right probability. This is about 7%. If we want a greater than, then we'll switch, click on this where it says right-sided, and then just change this number to 206,000, and then that gives us the right picture and the corresponding area and the probability. And then finally, for the one that is between, let's see if we can get this to work. We're going to click on interval. It froze. So I'm just going to refresh this. And we'll start over. That's fine. Let's see, so mean was 202.284, standard deviation 3,000. And now, let's see here, just change these two numbers, right? 200,000 and 205,000. This is about 60%, so about 0.5941. So you can see that's how I do the problem. It's a big word problem. So I try to write down what I'm given as soon as I've been given that, maybe even sometimes a sentence at a time, as you've seen that I've done. And then I take care to write out the probability that they're asking me for. Anyways, for me, this helps me think about what the picture ought to look like. And so I think the rest of these are just about the same there. It's just asking you for probability about a sample mean. So class, that is the first lesson in chapter 7. There's only going to be 2 of them. This covers sections 7.1, 7.2, and 7.3, and also 7.4. So this covers the first 4 out of 6 sections in chapter 7. Now that you've watched this video, please go out and immediately do the homework and the reading, if you haven't already, in the man textbook for those sections 7.1 through 7.4. Thanks everybody for putting up with me and for being here, or at least for viewing this. I hope you got what you needed to get out of this. And if you didn't get all of that, then again, this is another reason why we assign homework. Okay, please be out there practicing, and please be out there seeking help on any problem or concept that you don't understand.